Hi all. So once again I welcome all of you, and as I told you in last video, today I'll be discussing about periodic properties. But today I'm following a different method. First of all, let me discuss about theory part a little bit, then let's come straight to the problems. So that's the way we follow today. See, once we talk about periodic properties, it consists of three parts. First part, as you know, evolution of our periodic table. And second part, current periodic table. And the third part, periodic properties. So once we talk about the first part, what are the different concepts? The first concept, what we can talk, nothing else, Dauberniers triad. So first part, there is no doubt, Dauberniers triad. And what is Dauberniers triad concept? He formulated a group of three elements which are similar in properties. Like, I can write some examples. We have first of all lithium, sodium, potassium. Similarly, we can write chlorine, bromine, iodine. See, he formulated such group of triad. What the speciality of these triads? These elements which include in this triad, they are similar in properties. And what about the other speciality? So definitely you know that. What is the atomic weight of lithium? It's 7. What is the atomic weight of potassium? It's 39. And what is the average of these two weights? So let me find out the average of these two. 39 plus 7 divided by 2, which will be equals 46 by 2. So we get 23, and this 23 is the atomic mass of the middle element. So the first concept introduced by Daubernier. And what is Daubernier concept? So Daubernier formulated a group of three elements which called as triad. And what the speciality of this triad? All the elements in this triad are similar in properties. At the same time, the atomic mass of the middle element is average of other two. And I have written two examples here: lithium, sodium, potassium, first example. Then chlorine, bromine, iodine as the second example. And these two are example for vertical triads. And suppose if somebody asks you what's an example for a horizontal triad. So please try to understand, we have one more concept called a horizontal triad. We have example nitrogen, oxygen and fluorine. So this is the first concept called the Dauberniers triad. See, we have a second concept. Second concept introduced by Newlands. And what is Newlands Law of Octaves? So, actually Newland arranged the elements in the increasing order of their atomic weight. Let's see how he arranged. See, hydrogen, and after hydrogen, helium. It's a noble gas. It's not discovered by that time. So after hydrogen, we have a lithium. Then we have a beryllium. So next boron, next carbon, nitrogen, oxygen, fluorine. Neon is not discovered by the time. So after that, we have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. And after that, we have potassium, calcium, then we have scandium. See here, what is observed? See, every eighth element is similar in properties with the first one. See, for example, sodium is similar to that of lithium, and magnesium is similar to that of beryllium. Aluminium is similar to that of boron. So this is the concept introduced by Newlands. But what's the drawback of this concept? This is applicable only to lighter elements, or if we say it is applicable only up to the elements with atomic number 20. So these are the two important concepts what we need to know. First one, I have told you Dauberniers triads, And the second concept I have told you, Newlands Law of Octaves. And we have two more concepts. Actually, they have just mentioned regarding one concept in NCERT, but we don't have much more to talk about that. And that concept is called Lothar-Meyer atomic volume curve. So I'm just writing here, what is the next concept? Lothar-Meyer atomic volume curve. So Lothar-Meyer atomic volume curve. So what is Lothar-Meyer atomic volume curve? See, it's a curve like this. He plotted a graph connecting atomic volume against atomic mass. Then he could see that similar elements occupy identical position in the graph. Once you analyze this graph, you can see that alkali metals, they occupies the apex of the graph, isn't it? Alkaline earth metals, they occupies the descending portion of the graph. And halogens, they occupies the ascending portion of the graph. This is the concept introduced by Lothar-Meyer. So we have three concepts already. First one is Dobrnier's triad, and the second one is Newlands Law of Octaves, and next is Lothar-Meyer atomic volume curve. And what next? Actually, we need to be familiar with this term. It's not mentioned in NCERT. It's called Decan-Courtois telluric helix. See, I'm just showing Decan-Courtois telluric helix here. See, this name and the scientist name you should be familiar with. So this is the initial part of the evolution of our periodic table. So let's go with the second part of our evolution of periodic table. You know, the most important contribution made by whom? It's by Mendeleev. And he only knows as the father of periodic table. And for that only he got the Nobel Prize. So let's see what are the different concepts introduced by Mendeleev. So you can see a Mendeleev periodic table here. And once you analyze, you can see that how he arranged the elements. So first point, he arranged the elements in the increasing order of atomic weight. So he arranged the elements in the increasing order of atomic weight. Second point, it consists of certain number of horizontal rows and vertical columns. You know, for these horizontal rows, we call it as periods, and for vertical columns, we say as columns. Group, isn't it? How many groups and how many periods are there? So it consists of 7 periods. Mendeleev periodic table consists of 7 periods and 8 groups. So these 8 groups are numbered as 1 to 7 are again categorized as A and B, and 8th group as such. Now, actually this is structure of initial Mendeleev's periodic table. But after the discovery of noble gas, then later one more group was added as a 0th group. Now, so this is the structure of Mendeleev's periodic table. First point, it is based on the increasing order of atomic weight of elements. It consists of 7 periods and 8 groups. These 8 groups, out of these 8 groups, 1 to 7 are categorized as A and B. Later, after the discovery of noble gas, one more group was added as a 0th group. Now let's see what about the merits and demerits. First of all, let me number merits. So first merit, this was the first systematic periodic table. So the first merit, this was the first systematic periodic table. Second point, he could correct the wrongly assigned atomic weight of certain elements. Like, you know, at that time beryllium was assigned atomic weight of 13. When he arranged the elements in the increasing order of or arranging in the order of property, he could see that beryllium position is not matching. So by using this concept, he could correct the wrongly assigned atomic weight of certain elements like beryllium, indium, gold, platinum. So what is the second point? He could correct the wrongly assigned atomic weight of certain elements. Example, beryllium, gold, indium, platinum. Third point I think almost all of you are familiar with. He could correct the atomic weight of certain elements definitely. And third point, he could predict the properties of certain elements, and also he left vacant spaces for those undiscovered elements. So he left vacant spaces for the undiscovered elements, and also he predicted the properties of these elements. You know the examples for them? You know, it is called Eka aluminium. And what is next? Eka silicon. Isn't it? What is next called Eka boron? What is next called Eka manganese? So he left vacant space for the undiscovered elements. At the same time, he predicted the properties of those elements. Examples: Eka aluminium, Eka silicon, Eka boron, Eka manganese. What is Eka aluminium? You know, Eka aluminium means gallium. And what is Eka silicon? It's germanium. What is Eka boron? It's scandium. What is Eka manganese? It's technetium. You know what the specialty of technetium? This is the first artificially prepared element. So these are the merits of a Mendeleev's periodic table. Now let's talk about Mendeleev's periodic table demerits. See, first demerits, you know, it is based on the increasing order of atomic weight. But, you know, isotopes. Isotope means the species with the same atomic number but different mass number. So for example, for hydrogen, you know, you have three isotopes: protium, deuterium, tritium. Mendeleev didn't assign any separate position for these isotopes. That's the first drawback. So no separate position for isotope. No separate position for isotopes. Second point, that's still a controversy. You know, it's regarding the position of hydrogen. Where to keep this hydrogen? Along with alkali metal or with halogen family? Still it is a controversy. Similar to that time also you have the same problem. So position of hydrogen. Position of hydrogen. Third point, he arranged the elements in the increasing order of atomic weight, but in certain occasion this order is not strictly followed. Say for example, we have argon and potassium. Here the increasing order of atomic weight is not followed. Cobalt and nickel, tellurium and iodine, thorium and protactinium. In this occasion, the increasing order of atomic weight is not strictly followed. And fourth drawback, you know, similar elements have to arrange in a particular group only. But in this periodic table, at certain occasion, dissimilar elements placed in similar group and the same elements placed in different groups. That's the demerits of Mendeleev's periodic table. Now let's come to the second part of our chapter. It's nothing else regarding modern periodic table. Modern periodic table, also known as long form periodic table or Bohr's periodic table. See, what about the structure of our periodic table which I have shown here? See to that. Our periodic table consists of 7 periods and 18 groups. First group, alkali metal. Second group, alkaline earth metal. See, why we call it as alkali metal? Because their metal oxides are basic in character. Second one, alkaline earth metal. Why we call them as alkaline earth metal? Their oxides are alkaline, at the same time they exist on earth crust. Now 3 to 12, they are called as transition elements. You know why they are called as transition elements? As the elements' properties are gradually undergoes transition from metal to non-metallic character, or electropositive to electronegative character. 12th group, it's called atypical elements. Now 13, it's called as boron family. 14, called as carbon family. 15, called as nicogens. Why they are so called? They are foul smelling producers. 16, they are called as chalcogens. Why we call them as chalcogens? Because they are producing ores. Next, 18, halogen, salt producers. 18th, noble gas. Now let's see regarding their periods. See, how many periods are there? 7th periods are there. So first period, how many elements are there? In first period, you have only 2 elements. In first period, you have only 2 elements. See, why you have only 2 elements? Why you have only 2 elements? Because it corresponds to filling of electrons only in 1s orbital. See again, right? First period, only 2 elements because it corresponds to filling of 1s orbital. Similarly, we can come down. Second period, how many elements are there? 8 elements are there. Why 8 elements are there? Because it corresponds to 2s and 2p. So that a total of 8 elements can be occupied there. Now third period, how many elements are there? Again 8 elements are there because it corresponds to 3s and 3p. You may ask one question, why 3D is not included there? 3D can be filled only after the filling of 4s. So we have a fourth period can start with 4s. So after 4s, it's 3D, then what you get there, 4p. So as a total, you will be able to accommodate 18 electrons here. Similarly, for fifth period, how many elements can be arranged? Again, 18 elements can be arranged because it corresponds to 5s, 4d and 5p. Similarly, for sixth period, how many elements can be arranged? Let's see what are the orbitals used there. The orbitals used is 6s and 4f, 5d, 6p. Means you can accommodate a total of 32 elements. Similarly, for seventh period also you can accommodate 32. So we have 7s, 5f, 6d, 7p. So this is a summary regarding groups and period of our long form periodic table. And see some more points here. First group and the second group, these together called as S block element, because you know that their electrons enter into s orbital. Now 12 to 18, these groups are called as P block. These are called as P block because their last electron enters into p orbital. And 3 to 12, they are called as transition elements, or we call it as D block element. So we call this as D block element. So now one more block is left with. It is F block. So where F block start with? See, in sixth period, we have how many elements? 32 elements. So now only one block is left with. It's F block. So from where F block start with? See here, we have a sixth period. How many elements are there? 32. And in this 32 element, once you check the atomic number, you know lanthanum, what's the atomic number? 57. And after lanthanum, you know what element comes there? It's hafnium. So what is the atomic number of hafnium? 72. So in between 57 and 72, how many elements are missing? 14 elements are missing. And those 14 elements we have kept at the bottom of the periodic table to limit the size of the periodic table. So those elements, you can see that it starts with lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium. In that way, it's up to lutetium. So, you know, these elements, in these elements, electrons are entering into F orbital. So we call this as a F block elements. And this series follows lanthanum. So we call it as lanthanoid. So what is this series name? Definitely we know that it's lanthanoid. Similarly, once you see below this, below lanthanum, you know actinium. What is atomic number of actinium? 89. And after actinium, you are getting rutherfordium. What is the atomic number of rutherfordium? 104. In between this also we have 14 elements, and that 14 elements we kept at the bottom of lanthanoid, and what we call for that? Actinoid. So lanthanoids and actinoids consist of a D block. So we have S block, D block, P block, and finally we have a F block. This S and P together known as representative elements. S and P block together called as representative elements. Representative elements. Now let's see what are the important characteristics of different blocks. We have S block, P block, D block, and F block. First point we need to know regarding their general electronic configuration. So what you can talk about S block? Their general electronic configuration comes as NS1 or 2. And what about these elements? You know, in S block you have some members: lithium, sodium, potassium, rubidium, cesium. All these are metals. And you know, when you keep sodium or potassium in water, they catches fire. So they are highly reactive. So what are the character of S block? All are metals. So all these elements are metals, and they are highly electropositive. They are highly electropositive, and they are highly reactive, as I told you. And what about their oxides and hydroxide? You know, sodium hydroxide is basic in character. Lithium hydroxide is in basic in character. Calcium hydroxide is in basic in character, as well as their oxides also basic in character. So you can write there, their oxides and hydroxides are basic in character. These are the character of S block. Similar to that, let us think about P block. Can we say that all these are metals here? No. Nitrogen is not a metal. Nitrogen is a non-metal. Silicon, it's a metalloid, isn't it? So it consists of metals, non-metals, and metalloid. If we talk about aluminum, it's a P block, but still it's a metal. So it consists of metals. Next, we have metalloids, and next we have non-metals. What is the general electronic configuration? Here we wrote NS1 or 2. What we need to write here? NS2, NP126. And what about their properties? most of them are electronegative. So let's write the next point. They are highly electronegative. If we think about oxygen, nitrogen, fluorine, they are highly electronegative elements. And what about d orbital? What about d block? So there we have a electronic configuration n-1 d1 to 10 ns0 to 2. It consists of only metals. It consists of only metals. And we know we'll definitely study about this in another chapter called the transition element. But still, you know some of the properties of these elements. They form colored compounds. They form coordination compounds, isn't it? So all these are characters of D and F together. So let's write only their general electronic configuration. So what is the general electronic configuration of F block? N-2 F 1 to 14 n-1 d 0 to 1 ns 0 to 2, and it also consists of only metals. So these are the general properties of S to F block. Let's come to the third part of our chapter, periodic properties. Actually, we have 4 important periodic properties to talk with. First one, size. Second, ionization enthalpy. Third, electron gain enthalpy. And last one, electronegativity. So let me talk what are the important points regarding atomic size. As you know, atomic size can be expressed in covalent radii, or we have atomic radii, or we have a van der Waals radii. So the first point you need to mind, see, regarding their radius. We know R covalent will be smaller than R atomic will be smaller than R van der Waals. So this is the first point that you need to keep in mind. R covalent is smaller than the real atomic radius, and van der Waals radii will be bigger than the atomic radius. Why covalent radius is smaller than atomic radius? Because during the formation of an atom, during the formation of a molecule, atoms are combining together. So during that combination, some small portion will be encroached, isn't it? So that the covalent radius will be smaller than atomic radius. And you know, in case of van der Waals radii, we are taking too much bigger size. So the first point you need to keep in mind. Second point regarding atomic radius, R plus is smaller than Ra smaller than R minus. What is R plus? Radius of cation. What is Ra? Radius of atom. What is R minus? Radius of anion. So radius of anion is bigger than the radius of atom, and radius of atom is bigger than that of radius of cation. You know why the radius of cation is smaller than the radius of atom? Because if we remove one electron, the net pull on the valence electron will be more in that way. Anyway, we are not going to discuss that in detail. We are saying the important points. Next, see, regarding the isoelectronic species. See, when we talk about isoelectronic species, you know, I'm just writing some isoelectronic species here. See, we have first of all N3 minus. What is next? O2 minus. Next F minus. Next Na plus. Next Mg2 plus. See, I have written some isoelectronic species. Once we move from left to right, see, from here to there, what happens? Atomic number increases. So atomic number increases means nuclear charge increases. They are isoelectronic species. Valence electron is same only. As the atomic number increase, their nuclear charge increase. And if the nuclear charge increases, effective nuclear attraction increases. Hence, what will happen there? Size decreases. So what about here? So the first point regarding atomic size, radius of cation is smaller than atomic radius and van der Waals radii. Then R plus less than R atomic less than R plus, R minus. Then for isoelectronic species, you have got like this. What is the next point? Next point. Once we comes down the group, what happens with the atomic size? Down the group, size of the atom increases. And next point, along the period, size decreases. These are the points what you need to remember regarding the atomic size and its periodic properties. Now, let's think about ionization enthalpy. You know what is meant by ionization enthalpy? It's energy required to remove the most loosely bounded electron from an isolated gaseous atom. See, now we know what the definition. We don't want to spend much more time on that. What are the important points we need to keep here? First point, ionization enthalpy is always positive. That's the first point. See, first point regarding ionization enthalpy, it's always positive. Ionization enthalpy is always positive. What does it mean? Is it exothermic or endothermic? Positive means we need to spend energy, means it's an endothermic process. So please see to that. It's always positive means it's an endothermic process. It's an endothermic process. See, they are giving one option here, like M gives M plus 1 electron. And whether they are asking this process is exothermic or endothermic. Definitely we know that we are ionizing the species. So ionization means removing one electron. So this is an example for endothermic process. So that's the first point we need to remember regarding ionization enthalpy. Second point, please try to understand IE3 is always greater than IE1. There is no exception to this rule. Whoever comes, even if it's second group, third group, whatever comes, you can see that IE3 will be always greater than IE2 will be greater than IE1. And third point, see to the third point, which one has higher ionization enthalpy, which one has lower ionization enthalpy? This is the point to be discussed next. So here I am drawing a table. See to that. See, we have a maximum and minimum. See, I am writing first of all IE1. Next, I am writing IE2. Next, I am writing IE3. See, which one has maximum IE1 and minimum IE1? Which one has maximum IE2, minimum IE3? Similar type of questions can be asked. So what I am writing here, see, I1 maximum for noble gas. So I am writing here 0. If you write here 0, the next numbers can be easily predicted. Add 1 everywhere. So here it is 1. Here also 1. Here add 1. So it will be 2. Add 1. It will be 2. Here add 1 again. 3. Here add 1 again. So what will have? 2. So which one has maximum ionization enthalpy? It's maximum IE1, it's for 0th family. Which one has minimum IE1? It's for 0th family. This table will help you to find that. Now the next point regarding electron gain enthalpy. See, when we talk about electron gain enthalpy, you know what is the definition of that? Is energy released when an electron is added to an isolated gaseous atom. See, I can write like this. M accepting one more electron, you are getting a M minus. See, I have told you earlier, wherever M gives you M plus plus 1 electron. This process is an example for endothermic one. So I told you very strictly this is endothermic. There is no doubt regarding that. But in this case, we have a slight problem there. Generally we say this is energy released when an atom accepts one electron to give an ion. That's what called electron gain enthalpy. So we may say that electron gain enthalpy is an exothermic process, but always it's not like that. But generally you are right. Generally whatever you said, generally electron gain enthalpy is, so I'll just write like this. Generally electron gain enthalpy is negative, but not always. For whom it is positive? For noble gas, for beryllium, for nitrogen, for magnesium. Please remember this in mind. So for whom it is positive? Remember, for 0th group, next for nitrogen, next for beryllium, next for magnesium, this will be positive. Please remember that in mind. And next point, second electron gain enthalpy is always positive. Don't forget this point. So what next point? Second electron gain enthalpy is always positive. First can be either negative or positive, and I have told you in which case it is positive. For 0th family, nitrogen, beryllium, magnesium, it is positive. But for second electron gain enthalpy, it is always positive. And what's the trend here? Trend is exactly like ionization enthalpy. Once we comes down the group, ionization enthalpy decreases. So I'll just show the trend. Once we comes down the group, what happens with ionization enthalpy? Ionization enthalpy decreases. Similar manner, we can say that electron gain enthalpy also decreases. And here we know ionization enthalpy increases. Similarly, we can say that electron gain enthalpy also increases. So one more point to be noted here, that's regarding the halogens electron gain enthalpy. So we have fluorine, chlorine, bromine, iodine. So which one has the highest electron gain enthalpy? We normally say it's for fluorine, but it's not fluorine, that to be noted. So electron gain enthalpy of chlorine is greater than that of electron gain enthalpy of fluorine. So why fluorine has like that? You know, because of its small size, electron repulsion will be maximum. And so what is the correct order here? You can see that chlorine, and afterwards we have fluorine, then we have a bromine, then we have a iodine. In similar manner, you can see the next group. What about the next group? Oxygen, sulfur, selenium, tellurium. Here you can see the order. Sulfur has the maximum, then selenium, tellurium, then only who is coming there? Oxygen. Similarly for nitrogen family also same manner, but nitrogen has a positive electron gain enthalpy. So these are the important points regarding electron gain enthalpy. And now if you talk about electronegativity, so you know electronegativity is maximum for fluorine. And so electronegativity order, I can write like this. Fluorine has the highest electronegativity with a value 4. And next we have, after fluorine, we have oxygen. And after oxygen, it's chlorine, isn't it? So this order for the electronegativity of atoms. And these are the important points what we need to focus on. Okay. The rest is up to your preparation. So let me discuss some problems based on this. So now let's start with some questions. See here we have first question on board. which is the correct sequence of second ionization potential? See, while solving ionization potential, it is better to keep in mind one order. See, I'm just writing their order on board. See, the order comes like S1 less than P1, then we have S2, then we have P2, after that we have P4, next P3, next P5, and next P6. This is the correct order of ionization enthalpy sequence what we need to keep in our mind to solve this problem. So in that way, let us see what is the configuration of all these atoms. We have carbon, nitrogen, oxygen, fluorine. So carbon, where carbon comes, carbon configuration is here, P2. So this is for carbon. And next, nitrogen. So where nitrogen comes, it's P3. So nitrogen here. And what about oxygen? Oxygen here, P4. Next, here we have fluorine. So what is the correct order of second ionization potential? See, if they are talking about first ionization potential, you can follow this order. So this order I need to keep for first ionization potential. So what is the order of first ionization potential? Fluorine greater than, nitrogen greater than, oxygen greater than carbon. But they are not talking about first ionization potential, they are talking about second ionization potential. So let's see what is the second ionization potential. For carbon, earlier it was P2, but right now we removed one electron, so it becomes P1. So I need to show that carbon comes here. Next, oxygen. Oxygen, earlier it was P4, but right now it is P3. So I need to write oxygen here. Next, nitrogen, earlier P3, but right now it is P2. So I need to write nitrogen here. Fluorine, earlier it was P5, but as we are calculating second ionization potential, it is P4. So I need to write fluorine here. So what is the correct sequence of second ionization potential? Oxygen greater than, fluorine greater than, nitrogen greater than carbon. So which one is the right answer? You can see option 3 will be coming as your right answer. In this question also, the same manner we have to follow. They're asking about which one has the highest ionization enthalpy. I have told you to solve the problems related to ionization enthalpy sequence, what we need to keep in mind. Order, once again I am writing on board, S1 less than P1 less than S2, next P2, and after that P4, next P3, next P5 and P6. This is the order to be followed. Here we have boron, carbon, nitrogen, oxygen. They are talking directly first ionization enthalpy. So which one has the highest first ionization enthalpy? Let's see where boron comes. Boron electronic configuration. Boron is aluminum family. So it is P1. So here it is boron. Next, carbon. Carbon means P2. So here carbon. Next, nitrogen. P3. So here nitrogen. Next we have oxygen. Oxygen here. So which one has the highest ionization enthalpy? No doubt it's for nitrogen. So our answer here is nitrogen. So in this particular question, what they're asking with, hydration enthalpy of Mg2 plus higher than. See to that, what are the factors on which hydration enthalpy depends? So we can write the first statement, hydration enthalpy directly proportional to charge. That's the most important thing. Charge is of first priority. Second point, hydration enthalpy inversely proportional to size. So first priority you need to give for charge. In that manner, if you check it with Mg3 plus and aluminium 3 plus has higher charge. So they have compulsory higher hydration enthalpy than Mg2 plus. So these two are not our answer. So these two are not our answer. So in elimination round 1, 2 persons out. Now only 2 are competing there. We have a Na plus and B2 plus. See, even if you are not familiar with what is the hydration enthalpy of B2 plus, one thing can be understood. The charge of Na is only plus 1. Charge is less. Then compulsory hydration enthalpy of Na plus will be less than that of Mg2 plus. So who has hydration enthalpy of Mg2 plus will be higher than that of Na plus. So our answer is Na plus. Now you may ask right now, what about the hydration enthalpy of B2 plus? Let us compare. You know Mg2 plus and B2 plus. When you compare these two, both have a same charge. Okay, you can leave the charge matter. But what about that size? Size is smaller for beryllium and size is bigger for magnesium. If the size is smaller, again hydration enthalpy will be maximum. So who has higher hydration enthalpy? It's for beryllium 2 plus in this case. So our answer, hydration enthalpy of Mg2 plus will be higher than, see, Na plus. All other species have a higher hydration enthalpy than Mg2 plus. In this question, first ionization enthalpy of nitrogen and oxygen in electron volt. See, they had given some values. Definitely the intention of this question not to study the exact value of ionization enthalpy of nitrogen or oxygen. എന്ത് സാധനം എവിടെ കൊണ്ടുവന്നു ലിഫ്റ്റിലാ ഉള്ളിലേക്ക് പോയോ okay. So in this particular question, first ionization potential in electron volt of nitrogen and oxygen. See, they had given some values. Definitely we don't want to study the exact value of ionization enthalpy of any atom. We just need to know the order. So here the question, just to confuse you, you have to get the exact order, that's all. See, nitrogen and oxygen, who has the highest ionization potential? You know, nitrogen is of the order, or nitrogen has the configuration P3 and oxygen has the configuration P4. Who has the higher ionization potential? P3 has higher ionization potential than P4. This is the only knowledge what we required from here. So whose ionization potential is higher? Nitrogen has higher value than that of oxygen. So out of these two options, anyway your answer is not 14.6 and 14.6 because both are equal. Your answer is not 13.6, not 13.6, both are equal. So only two are left with. Out of these two, which one is for nitrogen? Nitrogen is first one. So first one should be higher. So in that way, what option you will be answer? Option A will be your answer. See, in this question, atomic radii of fluorine and neon in angstrom. See, it is exactly somewhat similar to the earlier problem, but there they are talking about ionization enthalpy, but in this case they are talking about atomic radius. See, atomic radius, anyway, fluorine and neon. You know fluorine, and after that fluorine atomic number 9, and after fluorine it's neon. See, why I drawn neon as a bigger atom? You know, neon is a noble gas. His atomic radius can be mentioned only in terms of van der Waals radii. But fluorine is not like that. Fluorine covalent radius or ionic radius can be calculated. So here fluorine radius is expressed in either covalent or in ionic, but in case of neon it's in van der Waals. So whose size will be bigger? No doubt its neon size will be bigger. So which one can be accepted? This cannot be your answer. This also cannot be your answer because the radius of both the atom cannot be equal, and only one option left with 0.72 and 1.60. See, fluorine is the first atom with a small radius and a neon is the bigger atom with the higher radius, and we know its radius is expressed in van der Waals radius. So our answer is this one, and most of the problem, none of this won't come as any option. See, in this particular problem, they are given N3 minus, O2 minus, F minus and Na plus. They're asking which one is smallest. See, by looking at these options, you can see that they are example for isoelectronic species. So I can write these isoelectronic species in their increasing order of atomic number. See, I'm just writing here. First of all, you have a N3 minus. Next, we have a O2 minus. Next, we have a F minus. And last, we have a Na plus. You know what is their atomic number? Atomic number for nitrogen, it's a 7, and for oxygen 8, and for fluorine 9, and for sodium it's 11. So once you move from left to right, their atomic number increases. If atomic number increases, their effective nuclear attraction also increases. If effective nuclear attraction increases, the size will be less. So size decreases. If the size decreases, who has the smallest size? Definitely sodium has the smallest size. So what is the correct order of size here? N3 minus greater than, O2 minus greater than, F minus greater than, Na plus. So who has the smallest size? It's for Na plus. In this particular question, they are given 4 elements. What about those elements? We can write carbon, nitrogen, and next we have a silicon and phosphorus. What is the correct increasing order of electronegativity? We know down the group electronegativity decreases. So I'll just write here, down the group electronegativity decreases, and along the period electronegativity increases. So who has higher electronegativity? We have a nitrogen has the highest electronegativity because it's on the right side and also its size is very small. Then you may have a doubt whether carbon or phosphorus, which one has a higher electronegativity after that. So first electronegativity highest for nitrogen, no doubt. And now among carbon and phosphorus, which one? Try to understand one point. Variation, decrease in electronegativity is more in a group than in a period. So when you compare phosphorus and carbon with respect to nitrogen, decrease in electronegativity more for phosphorus, but here decrease is less. So I can write next carbon, next obviously phosphorus, and the next we have a silicon. This is the correct order of increasing order of electronegativity. In that way, option 3 comes as your answer. So in this question, they are given different electronic configuration. Which one has the highest ionization potential? Okay, let's see to that. Here we can see that here the configuration is P1. Here configuration is P3. Here configuration is P2. And here again configuration is P3. But this is 3P3, 3P2, 3P1. And next we have 4P3. First of all, we can roll down see, let's write these elements first of all. What about these elements? 3p1, 3p2, 3p3. What are those elements? It is aluminium. Then we have silicon. Then we have phosphorus. And bottom to that we have arsenic. See, aluminium, silicon, phosphorus and arsenic. These are the elements given. Which one has the highest ionization potential? As we comes down, you know that ionization potential will decrease. So this is not our answer. So as we comes down, ionization potential or ionization energy decreases. So this is not our answer. And now if you go to that side, ionization energy increases. But there is some anomaly is there. But that anomaly favors phosphorus because it has a 3p3 configuration. 3p3 has very higher energy required because it is a stable configuration. So definitely you know that your answer will be neon 3s2 3p3 because it is half filled configuration, so that it will have a higher energy. So in this particular question, the correct order of ionic radii. See, they are given option by option. Let's see to that. Nitrogen, beryllium, boron. In a period, first of all, we have beryllium, then we have boron, then we have carbon, then we have nitrogen. Carbon is not there. Leave that. So beryllium has the biggest size, then for boron, then for nitrogen. This is the correct order. But this option is not in that way. So this is not our correct answer. Next, they are isoelectronic species. Let me write those isoelectronic species N3 minus, O2 minus and F minus. See, once you move from here, Z increases or nuclear charge increases, then size decreases. So who has the smallest size? F minus, then N3 minus. So this order is correct. Our answer is no doubt second one. Now, what about the problem with the third one? Third one, let me write in sequence. We have a lithium. Lithium, it's a first group member of group 1. Then we have sodium. Then we have potassium. So who has the bigger size? Definitely, lithium should have a smaller size. But that order is not followed here. So this is not our answer. Now next, Fe3 plus, Fe2 plus, Fe4 plus. Here we have a Fe. Next we have a Fe plus. Who has a smaller size? Fe will have a smaller size. Next Fe2 plus. Again we have removed one electron. So next Fe3 plus. So this is the order to be followed. So in that manner, this should have the smallest radius, isn't it? So here, this is also not the correct order. So only one option, it is the second option. See, in this question, which of the following has maximum number of unpaired electron? Here, let's see to that. What is the configuration of Mg2 plus? Mg2 plus means 1s2, 2s2, 2p6. Here there is no unpaired electron. In titanium 3 plus, titanium means scantium, titanium means it is 22. 22 means 3d2 4s2. So from 3d2 4s2 we have removed one electron. So 3d1 4s0. Here how many unpaired electron? 1. Similarly, vanadium, scantium, titanium, vanadium. 23 means 3d3 4s2. So from that we have removed 3 electron. So you will be getting 3d 4s. Actually it is supposed to be 3d2 4s2. We removed one electron from here. So we will be having a 3d2 4s0. So how many unpaired electrons? 2 here. And Fe2 plus. Fe means 3d6 4s2. And we have removed 2 electrons. So what we get there? 3d6 4s0. So unpaired electron 4. So where we have a maximum number of unpaired electron, we have a Fe2 plus. So fourth is the correct answer. So this is regarding the chapter periodic properties, and next class definitely will be going with some problems on states of matter. Till then, thank you.